Mainframes. These technological behemoths, often relegated to the annals of computing history, continue to power critical operations in industries like finance, healthcare, and government. For decades, they have been the bedrock of data processing, renowned for their unparalleled reliability, security, and transaction processing capabilities. Even today, as newer technologies emerge, mainframes remain indispensable, processing vast volumes of sensitive data and underpinning the digital infrastructure of our modern world. Despite their enduring relevance, the world of mainframes faces a significant challenge: a shrinking pool of skilled professionals who understand their intricacies. The languages used, often COBOL or assembly, are not as widely taught as modern programming languages. This expertise gap poses a threat to organizations reliant on these systems. Modernization is not just an option, it is an imperative. Mainframe modernization is not simply about replacing legacy systems, it's about unlocking their hidden potential. It's about enabling these robust machines to seamlessly integrate with modern technologies, allowing businesses to leverage the power of cloud computing, artificial intelligence, and advanced analytics. Modernization efforts can involve a range of approaches, from simple code refactoring to complete system replatforming. The choice depends on the specific needs and constraints of the organization. However, modernization is often a complex and daunting task. Legacy codebases can be vast and intricate, making them difficult to understand and modify. Traditional methods often involve manual analysis and rewriting of code, which is time-consuming, error-prone, and expensive. This is where large language models, or LLMs, are poised to revolutionize the mainframe landscape. Large language models trained on massive datasets of text and code are transforming the way we interact with and understand information. These models possess the remarkable ability to analyze, interpret, and even generate human-like text, opening up exciting possibilities for automating complex tasks. In the context of mainframe modernization, LLMs can be instrumental in code analysis, translation, and refactoring. They can help decipher legacy code, identify potential vulnerabilities, and even suggest improvements. Imagine an LLM trained on a vast repository of COBOL code. It could analyze millions of lines of code in seconds, identifying outdated programming practices, potential security flaws, and areas for optimization. This ability to comprehend and manipulate complex code at scale makes LLMs a game-changer for mainframe modernization. They can significantly reduce the time and cost associated with modernization efforts while mitigating the risks inherent in manual code manipulation. XMainframe is a purpose-built large language model specifically designed to tackle the challenges of mainframe modernization. It leverages the power of deep learning to understand and manipulate complex mainframe code, enabling a new era of automated modernization. At its core, XMainframe comprises 4 key layers: the data ingestion layer, the preprocessing layer, the model layer, and the inference layer. Each layer plays a crucial role in the model's ability to ingest, analyze, and generate code. The data ingestion layer is responsible for acquiring and preparing vast amounts of mainframe code for the model to learn from. This data can come from various sources, including legacy code repositories, documentation, and even expert knowledge. The preprocessing layer then cleanses and transforms this raw data into a format that the model can understand. This involves tasks such as tokenization, syntax parsing, and semantic analysis. The model layer, the heart of XMainframe, is where the magic happens. It's here that the model learns the intricacies of mainframe code, identifying patterns, relationships, and best practices. Finally, the inference layer allows users to interact with the trained model, providing insights, suggestions, and even generating modernized code. Training a large language model like XMainframe is a computationally intensive process that involves feeding it vast amounts of data and fine-tuning its parameters to achieve optimal performance. The training process leverages a combination of supervised and unsupervised learning techniques, allowing the model to learn from both labeled and unlabeled data. Supervised learning involves training the model on datasets where the desired output is already known, such as examples of legacy code and their modernized counterparts. This helps the model learn specific transformation rules and patterns. Unsupervised learning, on the other hand, involves training the model on unlabeled data, allowing it to discover hidden patterns and relationships on its own. This is particularly useful for tasks like code summarization, where the model can learn to identify and extract the most important information from a piece of code. The training process is iterative, with the model's performance continually evaluated and refined until it meets the desired level of accuracy and efficiency. From inference to deployment, XMainframe can be deployed in various ways to assist with mainframe modernization efforts. One common approach is to integrate it into existing development workflows, providing developers with real-time insights and suggestions as they work on legacy code. For example, XMainframe can be used to identify potential code vulnerabilities, suggest refactoring opportunities, or even generate unit tests automatically. This can significantly accelerate the modernization process while reducing the risk of introducing new bugs or errors. Another approach is to use XMainframe for batch processing of large code bases. This can be useful for tasks such as code migration, where the model can be used to automatically convert legacy code to a more modern language or platform. Regardless of the deployment scenario, XMainframe empowers organizations to modernize their mainframe systems more efficiently and effectively, unlocking the full potential of these critical assets. Navigating the technical labyrinth, the potential of XMainframe is immense, but its development and deployment are not without challenges. One significant challenge is the scarcity of high-quality training data. Mainframe codebases are often proprietary and difficult to obtain, making it challenging to train models that generalize well across different organizations and use cases. To address this, techniques like synthetic data generation and transfer learning can be employed. Synthetic data generation involves creating artificial but realistic datasets that mimic the characteristics of real mainframe code, while transfer learning allows models to leverage knowledge gained from related domains to improve their performance on mainframe-specific tasks. Another challenge is ensuring the explainability and trustworthiness of XMainframe's output. As large language models become more sophisticated, it can be difficult to understand the reasoning behind their suggestions or predictions. This lack of transparency can be a barrier to adoption, especially in risk-averse industries like finance and healthcare. To mitigate this, techniques like attention mechanisms and rule-based explanations can be incorporated into the model's architecture, providing insights into its decision-making process and increasing trust in its recommendations. XMainframe in action. A global financial institution, burdened with a massive and aging mainframe system, sought to modernize its core banking applications to improve operational efficiency and reduce maintenance costs. The institution faced a daunting task: millions of lines of COBOL code, limited in-house expertise, and a pressing need to minimize disruption to critical business operations. To overcome these challenges, the institution partnered with a technology firm specializing in mainframe modernization to implement XMainframe. The implementation involved training XMainframe on a vast dataset of the institution's legacy, COBOL code, documentation, and expert knowledge. The trained model was then used to analyze the code base, identify potential vulnerabilities, and suggest refactoring opportunities. XMainframe's ability to comprehend complex code and identify patterns that would have been impossible for human developers to spot at scale proved invaluable. The institution reported significant reductions in code analysis time, improved code quality, and a smoother transition to a more modern and maintainable architecture. Embracing the future of mainframe modernization, the advent of large language models like XMainframe marks a paradigm shift in the world of mainframe modernization. These models, with their ability to comprehend and manipulate complex code at scale, empower organizations to unlock the full potential of their legacy systems while mitigating the risks and costs associated with traditional modernization approaches. As large language models continue to evolve and mature, we can expect to see even more innovative applications in the mainframe space, further bridging the gap between legacy systems and the modern technological landscape. The journey towards mainframe modernization is not just about technological advancement, it's about preserving the invaluable knowledge and experience embedded within these systems, while embracing the transformative power of artificial intelligence. As we navigate this exciting frontier, collaboration between mainframe experts, data scientists, and large language model developers will be crucial in shaping the future of these critical systems and ensuring their continued relevance in the years to come.